This meeting is being recorded.
In section 5.2, we'll continue our discussion of stereoisomers, and we'll introduce a new definition, something called a chiral molecule. So say we do not have a ring or a double bond, we wouldn't be able to have a cis or trans isomer. This is only one type of isomerism as far as stereoisomers go, but we have other types of stereoisomers without double bonds or without ring structures, and these are called chiral molecules. So the term chiral means that the structure would be asymmetric, the compound is asymmetric. So if we reflected it in a mirror and then tried to pick up our original structure and put it on top of our reflection, they would not match. They would be what's called non-superimposable. So sometimes we can see this a stereoisomer result from a carbon that has four different groups attached to it. So we can determine whether or not two objects or two compounds are identical by reflecting them in a mirror and seeing if they are superimposable. If they are, they would be identical. If they're not, there'll be something called an enantiomer. So we'll learn this term in a later section, but just since I mentioned it, we'll write it out there. So what exactly is molecular chirality? Well, it's important for one, in biological or biochemical reactions, a lot of receptor sites or drug receptor sites are chiral. So not only are structures within our bodies chiral, but also certain pharmaceuticals or medications can have different properties depending on their configuration. So it may be hard to visualize mirror images of molecules and manipulate those in 3D space if you just draw them on paper. So drawing a 2D structure is sometimes more challenging. So in our stereochemistry lab, we've used these handheld models to help us as visual aids. So let's see, again, this concept of chirality. Let's get rid of this to start. So when a carbon atom has four unique groups, so that means that it forms four bonds, and each of those bonds are to something different. So in this first compound, we see the red group, the white group, the green group, and the blue group. So what we've done here is we have this mirror here, so we've reflected our molecule, and then we try to pick it up and put it on top of this molecule. So what we would find is that they are not superimposable, and we would call these structures the enantiomer of one another. So whenever you have a chiral compound, it will have exactly one enantiomer, one non-superimposable mirror image. So how can we find a chiral center or a stereocenter? So a carbon atom we'll specify here. There can be other atoms. We'll see some practice problems using phosphorus as well. But as long as the central atom or the atom that we're referencing is tetrahedral, it has four different groups, whether it's different atoms or lone pairs, we will consider that a chiral center. So let's take a look at this first molecule. We see this carbon atom here highlighted in green. So if we were to expand it, we would see that on this side we have an ethyl group, this side we have a methyl group. We can't forget about that hydrogen that is implied. And then we have this chloro substituent on top. So if we were to count, we have 1, 2, 3, 4 different groups. So that's how we determine this to be a chirality center, a chiral center. And we'll see that's the case here, right? We have our fourth group as a hydrogen, and like so here in this ring structure, we have the bromine, we have the hydrogen, so our highest priority here or lowest priority here. We'll talk about that prioritization later on as well. And then if we were to go around this side of the ring versus this side of the ring, we would see two different paths. So we would have 2 and group 3 here as far as priority go. So we have 4 different groups attached to this carbon. So we have, once again, a chirality center. So let's see if we could look at these compounds and determine how many chiral centers there are. So there's some ways to eliminate carbons right away. So if we have a carbon that's bonded to 3 hydrogens, for example, that would not be a chiral center, or even a carbon that's bonded to 2 hydrogens. As soon as you see more than one of the same group, you can eliminate that from being a chiral center. So that would be this carbon, this carbon, this carbon, etc. Right? All of these have 2 hydrogens bonded. So none of these that I just X'd out would be considered chiral centers. Let's take a look at this carbon here. So we might consider initially that this could be a chirality center, but we know that we need 4 different groups. So let's try here. Let's see. So this is my group 1. I also have a hydrogen, so that could be number 2. And then going around the ring this way and going around the ring this way, we see no difference. They're symmetric. So this actually would not be a chiral center either, because we would only have 3 distinct groups because of that symmetry within the molecule. If we were to look over here at this molecule, we could do the same thing. So now I have 1, I have a hydrogen, that's my second group. Going around the ring this way is different than going around the ring this way. So I will have 4 different groups and 1 chiral center here as a result. Let's take a look at this structure down here. So in general, it's a good idea to look for your wedges and dashes to see if they are stereocenters, and they would be considered chiral centers. So let's start on the right-hand side here. So we see this here has an ethyl substituent, a hydrogen, a methyl. So 1, 2, 3 different groups, and then all this over here would be our 4th group. So this would be a chiral center right here. Let's take a look at the second carbon, moving from the right now. So we have a methyl, we have 2 different groups on either side, and a hydrogen. So since it's not symmetric on either side here, we would count each of those directions to the left and to the right as different groups. So this is also a chiral center here. This site here, you may be tempted because of that wedge, right? We have a hydrogen, we have this portion of the molecule will be group 2, but then we have 2 methyl groups here. So that last carbon that has the wedge, this would not be a chiral center, so we still have only two centers here, right? 2 chiral centers. And let's take a look at this last structure here. So this going from left to right now. So down here we have this carbon here. So we have a methyl, we have an ethyl, we have a hydrogen, and then we have all this. So we have definitely 4 different groups from this first carbon. So that's a chiral center where that dot is. Moving next door to this site here, we have a hydrogen, a methyl, and then it's not symmetric, so we have 2 different groups. So this would also be a chiral center. Let's keep moving down. So here, this would not be a chiral center because we have a methyl, we have everything this way. We do not have a hydrogen. We only have 3 distinct groups because of this double bond. So this last dot here, this would not be. And then we move to this carbon here. We see the same thing. We see only 3 distinct groups, a methyl, a hydrogen, and then the double bond to the carbon. So that one's eliminated. And then this spot here has 3 hydrogens. So we can eliminate that last carbon on the end as well. So our last result would be 2 chirality centers here as well. So let's take a look at this next slide, and we see that we have no chiral centers, 2 chiral centers, and for the remaining 3 compounds. All right, so we will continue. Let's continue with this one here, right? So we have this larger structure, this vitamin D. So we can go through, we can eliminate any CH3s, any CH2s, and any carbons in general that do not have 4 bonds. So, so we can eliminate here, here, right? This has 2 methyl groups. We know that these all have 2 hydrogens. This carbon's eliminated. What about this site here? So we know that we have going this way, a different group than going this way. We have a hydrogen, and then we have this, this methyl substituent. So this will be our first chirality center in that circle. Let's see, then we have this carbon here that has 4 different groups. Let's see, 1, 2, 3. These all have multiple hydrogens, so we can eliminate those, where all these X's are, etc. Right? So we can go through our compound. We can see if we have more than 1 hydrogen, eliminate it immediately, and we would end up determining our total number of chirality centers using this method. So we have 1, 2, let's see, this will be another one, right? Because we have a hydrogen there, and going around our ring gives us 2 different results. So we have 1, 2, 3. Oh, this one here would also be a chirality center. So this term enantiomer I've used previously to define a non-superimposable mirror image. So, so we have our chiral compound here, we have our mirror here, and we want to reflect this compound. So we would show the mirror image something like this. If we were to reflect this horizontally into this mirror, and this will be the enantiomer. So you can do different reflections of your compound, whether the mirror is placed next to it, behind it, or below the compound. So depending on where your placement of your mirror is, you would generate your reflection in different ways. But no matter which way you reflect it, we can only have 1 enantiomer. So the enantiomer is shown here for this compound. So when we look at enantiomers, I mentioned that we can put a mirror behind our compound. So that's what we're shown between these 2 enantiomers here. If the reflection of this compound with the chiral center on a wedge, this is coming out towards us. If we were to reflect this in a mirror behind it, it would look like this was on a dash in that mirror. So the only thing that changes when we draw the enantiomer using a mirror behind will be to place anything on a wedge on a dash. Right? So that's where we have our enantiomers there. And like so, this is also a reflection. If the mirror was behind this molecule, we would end up with this enantiomer, and again down here. So all we have to do is, this one's actually not a chiral compound, right? Because if we were to count our groups, we have symmetry here. So this one is not chiral, and inverting our wedges and dashes would actually just generate the same structure here. So be careful, look for symmetry, make sure that you have 4 distinct groups before you attempt to draw an enantiomer. So we will continue and start designating priority using the Kahn-Ingold prelog system in our next video.